Well, in the last class we had begun to look at the polymers which are non-crystalline generally, and we saw some of these long chain polymers. Because network polymers, there is no chance for us to get any crystallinity in them, and continuing with that, we ended up with elastomers. We shall now look at the mechanical behavior of elastomers. Well, as you recall, I said the elastomers or the polymers which behave like elastomers, they have the chain segments having translational mobility at room temperature. There is a natural tendency for bending and coiling that we express with the help of the monomer unit of polyisoprene. And then there are few crosslinks. Here I show you the crosslinks. In the lower picture, the crosslinks are just one molecule or maybe one atom or something which is between the two chains, like that. And here are smaller molecule or smaller chains which are the acting as crosslinks, the gray colors, like this. Okay. So the crosslinks can be made with the help of small molecule polymers as well, or smaller chains, and it can also be made with the help of, like I showed, the vulcanization of the natural rubber, we use sulfur. Okay. So besides being the long chains, they have to satisfy these conditions, that there are few crosslinks, there is a natural tendency for bending and coiling, and then the room temperature provides enough mobility to the chain segments. That's a translational mobility I am referring to, because in solids oscillations are always present. Now when we look at the mechanical behavior of an elastomer, it is quite distinct from other materials which we will be talking about a little later. If I have to test under stress or under force a material like a metal, steel, and which is an alloy, or copper or aluminum, I will get elastic elongation not exceeding 0.5%. It will be 0.2%, 0.15%, things like that. But here I get a few 100% of temporary deformation, which is recoverable deformation. In other words, when I remove the force, the elastomer comes back to its original shape and size after it was extended by the force to the tune of 400%, it comes back, which is not the case in other metals and alloys or other solids. Secondly, the deformation process is non-linear. Elastic behavior, whether it is of steel or aluminum or any other material for that matter, would be obeying the Hooke's law. That's a linear elasticity. Stress is proportional to the strain, but here it is non-linear. It is not linear. And a third difference with other materials is, if you take a piece of aluminum or steel, which is you apply the force and extend it, and then you increase the temperature from room temperature to, let's say, 200 degrees centigrade, then you will notice a further elongation because of the thermal expansion. But in here, if you increase the temperature by a few degrees, you will find it starts to contract. So you will find that on heating, a stretched elastomer contracts. This property has given rise to making rubber engines, which converts the low grade heat, that is at low temperatures, and can be converted to a mechanical energy. Okay, so these are the differences, and we shall try to see this knowing the structure of the elastomer and looking at the thermodynamics. Some of it we have already seen. Combined first and second law of thermodynamics can be written as du is equal to TdS minus dW, where TdS is the term which has the heat input and dW is the work done by the system. Heat is input to the system, work is done by the system, and the difference of this is the increase in the internal energy of the, it's basically conservation of energy. And then we also define the Helmholtz free energy, E is equal to U minus Ts. Elastomer is a solid, and once again PV term is going to be negligible, and therefore I can talk about the Gibbs free energy or the Helmholtz free energy. Here I am talking about the Helmholtz free energy, which can be written as U minus Ts. Now at a constant temperature, when I try to differentiate this, I get delta E at constant temperature is equal to delta U at constant temperature minus T delta S at constant temperature. Temperature is constant, I don't have to differentiate that. So now this number at constant temperature, I can write this from the combined first and second law. When I do that, it can be written as T delta S at constant temperature minus dW at constant temperature minus T delta S at constant temperature. First term and the third term cancel with each other. I am left with this, the middle term, where W is the work done by the rubber or the system. With a minus sign in front, it is the work done on the system. So at a constant temperature, when I try to stretch the rubber, I apply the force F. The rubber elongates by a distance, let us say delta L. Not change the temperature, room temperature only. So work done by the force is F delta L. Right? That's what this minus dW would be at constant temperature. Since the condensed system, as I already said, this is negligible, so this work is the work done by an external agency. So that's what I said, the work done by the external force in extending the rubber by a distance delta L is F delta L. And if the work done by the elastomer is minus of that, it's because the work is done onto the elastomer in stretching it. So therefore work done by the elastomer, W we said is the work done by the elastomer, can be written as minus F dL. So delta you write D because you are writing as a derivative. Right, we said delta E at constant temperature is minus delta W at constant temperature, previous slide, right, and dW is minus FdL. So I can write this minus and minus go away, become plus, right, is F delta L at constant temperature, right, because we wrote that delta E at constant temperature is equal to minus delta W at constant temperature. That's the last slide if you recall. So if I substitute that here, I get this F delta L at constant temperature. Well, this can be rewritten because I have talked about this only the total derivatives at a constant temperature, which you can also say at a constant temperature then it becomes a partial derivative. F can be rewritten as at constant temperature dE by dL, and E I have already defined as U minus Ts. So if I differentiate that, delta U delta L at constant temperature, the right hand side, minus temperature is constant, T is constant, delta S by delta L at constant temperature. Well, if you write E, its total derivative, like this dE du minus TdS minus SdT, because it is u minus Ts. du minus TdS minus SdT. du can be written from the combined law TdS minus dW, and dW in this case should be written as minus FdL. So, I make it plus and write it FdL, and then other terms minus TdS minus SdT. So, this TdS first term cancels with the third term here, and I am left with this FdL minus SdT. Is this clear? All right. And that is what we wrote, dE is equal to FdL minus SdT. This shows that E is considered, if it is a total derivative written like this, is a function of L and temperature. If I have a variable which is a function of two other variables, this function can be differentiated, and total derivative can be written as delta E delta L at constant temperature into dt plus dl, sorry, you are right, it should be possible for me to. And plus delta E delta T at constant length into dt. If I compare this expression with this expression, I get delta E delta L at constant temperature is nothing but, and when I compare the second term, delta E delta T at constant length is equal to minus of S. Right. I try to work out the second derivatives like this, delta square E delta L delta T. It can be brought from here by differentiating this number delta E delta delta T delta E delta L at constant temperature. The whole thing is differentiated at constant length here. That means I have to differentiate this right hand side with respect to T at constant length, and that becomes equal to delta F delta T at constant length. Similarly, from here I can get this derivative as delta delta L of delta E delta T at constant length, and put this at constant temperature. That means I must differentiate the right hand side with respect to length at constant temperature is minus delta S delta L at constant temperature. So, this becomes equal to, from there, delta F delta T at constant length, and is also equal to minus delta S delta L. This is something equivalent to Maxwell's relations which are done in gases in thermodynamics. But the important thing what we notice here is this second derivative, once I write force with change in force with change in temperature at constant length, I maintain the constant length of the elastomer, change the temperature, see what is the change in force required to achieve that. Similarly, here it is entropy which is related to the length of the elastomer at a constant temperature. Now, the importance of getting this information is the first derivative on the left I can experimentally measure. I can measure force, I can measure temperature, I can measure length. So, therefore, I can measure this, and you will be performing this out of this first set of minus, the second set of experiments, we will be doing one experiment on this. But if you look at the right hand side, the delta S, delta L, you cannot measure entropy with respect to length, you cannot measure entropy at a temperature. There is no easy way of measuring entropy of the rubber. But when it comes to seeing the arrangement of chain segments which are coiled, which are cross linked, how are they placed in the given volume, you can find out the number of configurations and you can model out the configurational entropy. Since it is a constant temperature, there will be no change of thermal entropy. So, you can model out the configurational entropy. From there you can write down this derivative delta S by delta L at constant temperature. So, modeling can be done, that is the right hand side. Verification of that model can be done by measuring the left hand side through the experiment. That is the great advantage of getting this relationship, and that is what I am to show you now next. Well, in an experiment it is also possible for you to measure the change in internal energy at a constant temperature, the elastomer. And if you write this, it turns out to be U is TdS, so it turns out to be constant temperature, it is T delta S delta L at constant temperature minus dW, which is the work done on the rubber delta L by delta L at constant temperature will become this. That is the combined first and second law I have differentiated already. Experimentally, when we measure, I cannot measure this as I already told you. What I will be measuring experimentally is minus of T times delta F delta T at constant length plus F. Because delta S delta L at constant temperature is equal to minus delta F delta T at constant length. And this also you will measure in an experiment, because this is measurable in experiment, this is measurable, that is measurable, and that turns out to be approximately 0. Of course, you will get that within your experimental errors.
So, what is force here?
Force is the force applied on the elastomer. So, you have take a rubber band, you stretch, you are applying some force to stretch it. If you do not apply that force, it comes back to its original shape. And we are talking about the thermodynamics when the rubber is already stretched after applying some force. And it is the thermodynamics of stretched elastomer we are working out. Okay. So, once this is 0, it can be rewritten this from here as F is equal to minus T delta S delta L at constant temperature, or it can be written as F is equal to T delta F delta T at constant length. Here it is a minus sign, there it is plus sign. And in here S is the configurational entropy, because I am maintaining the temperature constant, there is no change in the thermal entropy. And the stretching we are doing isothermally, and the configuration entropy we had written earlier as is equal to K log W. This W is not the work here, W is the number of configurations. right? And this number of configurations have been modeled, been worked out for us. We shall not go into the details of that. Right. S minus S0 can be written as K natural logarithm of W by W0. Right. So, this is the reference state, W0 is for the reference state, S is the stretched rubber state, and W is the state of the stretched rubber. All right. So, that is the configuration difference in the configurational entropy, which I will get delta S. When I differentiate S0, the reference state is going to be constant. So, I can always talk about when I differentiate this, I have been differentiating basically the S. So, this model has been worked out for us. I am not going to work it in details, and some research it was done. Of course, some assumptions are involved in here, and from the formula which got F is equal to minus T times delta S delta L at constant temperature, I can differentiate this with respect to length at constant temperature and see what do we get. So, this derivative delta S delta L at constant temperature from this expression minus 1 by 2 N0 K, the Boltzmann constant. This L square when they differentiate becomes 2L divided by L0 square. When I differentiate this, it becomes minus 2 L0 by L square, and constant does not give me anything, that gives me 0. All right. So, this we can further simplify. I don't have a place to do that. I can take L0 out, then what it gives me is minus of 1 by 2 N0 K by L0, and 2 also taken out. So, this 2 will cancel out there, I will be 1 left with 1, it will be L by L0 minus L0 by L whole square, it would be a little different way of writing it. And when we go back to this F, I have to multiply it by minus T, this minus sign will also go and T will come in the numerator. So, F will be equal to N0 KT by L0 in bracket L by L0 minus L0 by L whole square. So, this is where I get from here. That is my F. Now, I have related the force to the original length of the elastomer, stretched length of the elastomer, and the T, the temperature. Applied force, stretching of the elastomer, and the temperature. These have been related. This is called the equation of state of the elastomer. That is what you have got. F is equal to N0 KT by L0, L by L0 minus L0 by L whole square. If this is the equation of state of the elastomer, any equation of state must be single valued and continuous, for the simple reason My rubber is not an imaginary item. My rubber does not evaporate. My rubber is there where it is. When I apply a force, a little more, little less, it is there. So therefore, it must be a continuous and single valued function. This can be rewritten as a function of force, length and temperature. N0 in here is the number of cross links in the given piece of the elastomer. N0 I think should have defined is the number of cross links. It is not the Avogadro's number, please. And if it say N0 by L0, it is the number of cross links per unit length of the elastomer given to you in the original state. Okay. So if this has to be continuous and single valued function, it must satisfy from the calculus a relationship that is delta F delta L at constant temperature multiplied by delta L delta T at constant force into delta T delta F at constant length, and the product should be minus 1. All right. This, if you want to work out as an experiment to test it, you will not be able to get this derivatives like this, but what you will be able to get is delta F delta L. Maintain a constant temperature, apply some incremental force. You have already stretched the rubber, and apply some incremental force, find out what is the increase in length. You got this derivative approximately. Then what you do is increase the temperature, right? Don't change the force, whatever force you had applied. Find out what is the change in the length, and as I said, rubber would contract. This would be a negative number. Force is not changed, right? You got that. Once you have done this, now bring it back to the original length which was there after applying the force delta F. Means whatever it has shrunk or contracted by, you extend it by the same amount at the increased temperature. So that shall give you delta T delta F. You have to know how much force you have to apply to come back to the length which was there after applying this stretching. Come back to there. So if you multiply these products, it should come approximately minus 1, because it's not the limit tending to 0, you have not worked it. That will say that yes, this is a continuous and a single valued function. Okay. This equation of state which is here available, if it is plotted, the stress, the force divided by the area of cross section, and the strain onto the elastomer here. It is non-linear, that is what we work out. And what the equation of state gives us is this path, which goes beyond here, dot 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 goes on. But what happens after about a few 100% of elongation, it starts to deviate from this equation of state and it goes in their direction, and where it becomes more and more steep, right? That is all what we have to see what it is. We have to explain that. Go back to an earlier picture here. Initially what is given to us is in a coiled state, the rubber is lying. Whatever maximum possible coiling can take place is taking place already. The configuration entropy is the maximum at that stage. Now when I stretch it, coiled states of the chain start to get uncoiling. On increasing the tensile stress or the force, they try to straighten out. But complete straightening is not possible. Why? cross links are there between various chains. They do not allow them to move very far off from each other. And chain segments are able to translate. Yes, it is possible for them to translate along with slightly and therefore readjust to get some straightening. The ultimate state, if it is possible for you to get to the straightened state, is this. And all chains are aligned parallel like this. What shall be the configuration entropy then? 0. In that state the configuration entropy would be 0. So you are decreasing the configuration entropy when you apply the stress like this, right. Now what happens when you are in this state, your stretched state, when it is uncoiled to some extent, there are secondary forces which come into play to maintain them in that state, with besides the primary cross links, and secondary forces are van der Waals forces. It is important for you to understand, because we know that configurational entropy is not a function of temperature. But when I talk of the configuration entropy, I have to talk about the number of configurations belonging to the same energy. What I am demonstrating here is, now the stretched piece of rubber, when I increase the temperature, what happens? These secondary forces which are there between the chains, the van der Waals forces, these weaken, or you can say they break, right. So since one of the forces which is holding them in this configuration is gone or reducing in strength, they try to coil back, because the primary cross links are trying to take them back. The applied force is trying to straighten it out, and then to maintain them in that state is being helped by the van der Waals forces. Out of the two forces, van der Waals forces and the applied stress, applied force, van der Waals forces have become weak, and therefore the cross links try to tend it back to coil. So the length decreases. This way, when we increase the temperature, you go to the configuration, coiled state configuration, more coiling, higher entropy state, right. So the point which I am trying to make here is, configurational entropy is not a function of temperature, but by changing the temperature, by increasing the temperature, in here what you have done is, you have changed the energy which belongs to the secondary bonds, the van der Waals forces. That energy is being increased. So you go back to, because that is the force which is holding in this configuration, and it is no more available, and therefore it goes to the state and it contracts back. It is not a very large contraction. You will be doing the experiment, you will see that it contracts. That is good enough to say that it contracts and we can make use of it. In rubber engines we do use this property of the rubbers. Alright, now when talk about this, I have uncoiled this, and during the process of uncoiling, coiled chain is uncoiled. I have not stretched any of the carbon-carbon bonds. It is only bent, and therefore coil is formed. So I just uncoiled. So there is no stretching of primary bonds. Would there be a change in internal energy? I am talking about the constant temperature. No increase in temperature here, not this. There would be no change in the internal energy, and that is the assumption which we have made in working out this equation of state which I showed you. I said delta U, delta L at constant temperature is 0. That you will also try to work out in your experiment. It comes out to 0 approximately, right. So that is the basic underlying assumption, that there is a stretching, there is only uncoiling of the coil change, there is no change in the internal energy of the elastomer. Now what happens? You are, as I said, you are not able to reach that state, because primary cross links are going to stop you. You cannot translate them permanently and make them completely straight. Once you have reached that stage, Now if you want to stretch it, what would happen? You would start stretching the primary bonds. Primary cross links are also primary covalent bonds. You will start stretching them, and that means you are tending towards Hooke's law, where the modulus of elasticity is very high, and that is what I was trying to say. What happens? Let's go back. When you are reached here, the primary cross bonds starts getting stretched, and this becomes steeper and steeper and steeper, where the Hooke's law will be obeyed. And if you do further anything, it may break. That can happen. So this is the part of the equation of state which we worked out under the assumption that there is no change in internal energy when a piece of elastomer is stretched. It is merely uncoiling of the coiled chains. Is the point understood? Right. That's now, if that is so, if I give you a piece of rubber, what you have, an eraser, and I have to put a weight of 10 kgs on it, measure the contractions or the change in size, and then heat it, will all the thermodynamics you have done will work there? Will it work? If I give you a piece of eraser, you have seen the piece of eraser, put a 10 kg weight on it. Why will it not work? Yes. The configurations are already there, the maximum possible coiling is there. Now when I put the force, compressive force, I am not stretching the elastomer, but I am trying to bring atoms closer. So I am affecting the primary bonds. So internal energy change will not be zero in such a situation. It is not uncoiling the coil chains, and there is no question of further coiling of the coil chains, they are already coiled, right. So therefore on compression, this analysis which we have done will not be valid because of the assumption that there is no change in the internal energy of the elastomer. Is that clear? Good. Now we shall look at the long chain polymers. Can they be crystalline? I started with these structures as non-crystalline. Most of the time they are non-crystalline. Particularly a network polymer, I said I can never crystallize it. It is always a non-crystalline structure. And same is true about the long chain polymers. They are most of the time non-crystalline, but it is possible for us to have partially crystalline long chain polymers, right. Partial crystallinity, let us see what I mean by partial crystallinity. Let us say in this small volume I have a few chains which are stacked parallel to each other, but since they are not of the same length, at the ends they do not remain parallel to each other because they are not of the same length. Then maybe another place, another set of chains are parallel arranged, but their ends again will cause the problems because they are not of the same length. And so on and so forth. So there is some volume of the material which where the chains are aligned parallel, they are crystalline, ordered arrangement. Rest of this is non-crystalline volume. That is why the partial crystallinity. If there is possible to have all chains of the same length and all parallel, yes, you will get 100% crystalline material, which is not the case, which is never the case. The other way they can arrange themselves, if I have a very long chain in a, let us say, a rectangular block like this, which is of course a thin block, these chains and then it can go backwards into the solid region. So, this region you see they are all parallel. In this region they are except the folds, the chain segments are all parallel, that becomes a crystalline region. Only non-crystalline region is at the folds, these folds become non-crystalline. And we have seen such kind of, this kind of structure, that kind of structure we have seen in polyethylene itself. Layers for layers, layers of layers, that means these chains are arranged like this. They can be peeled off because between the one layer like this and the second layer like that, there will be only van der Waals forces. One can be peeled over the other easily, peeling can take place. And here something like this is also seen in the flower patterns, that there are partial regions which are crystalline and more other regions are non-crystalline. So, this is how this crystallinity, if at all, is seen, is like this. It is partially crystalline. 100% crystallinity is not possible for a simple fact that no two chains are of the same length. Okay. And we can also try to align these chains by doing some mechanical working. I just talked about it yesterday briefly. You can cut a small strip from a container of this carrier bag of polyethylene, try to stretch it. If you start with a transparent material, after stretching you will see that it becomes opaque. It doesn't remain transparent anymore. You are trying to straighten out the chains by doing this, and also it is becoming a little more rigid. When the chains straightened out chain will be kind of a fiber where the chains are parallel, you try to stretch further. So, initial stretching you will find is easy for you, but later on you will find it becomes difficult for you to stretch it, and that becomes opaque. That is kind of working you can do, and if you do the working, chains can get aligned. That is one way of doing this. And also we have seen that when we want to see how much crystallinity is present in a polymer, we can measure its density, which is going to be more dense and which is going to be less dense. In non-crystalline region, all chains are zigzag, 100% non-crystalline. They are not going to fill the space efficiently, density would be lower. And when all the chains are parallel, they will fill the space more efficiently, density would be higher. So, what we find is in polyethylene, when I take a 50% crystalline polyethylene, its specific gravity is 0.93, and when it is 80%, it is 0.98. So, by measuring, and there is a linear variation of density and the percent crystallinity. So, once we make these measurements, it is possible for us to say after measuring the density of polyethylene how much crystalline it is. So, with this small kind of differences in density, one is called the high density polyethylene, the other is called the low density polyethylene. You have high density polyethylene bags, you have the low density polyethylene bags, all these things are available, right. Now, I have just talked about the chain lengths not being equal. We shall look at the factors that promote non-crystallinity in these long chain polymers. First of all is the length of the chain. Longer the chain means on an average, some would be longer than that, some would be shorter than that. There will be large variation of chain lengths, and there will be more entanglement of chains, and there will be more crystallinity, non-crystallinity. It will not become crystalline if the chain lengths are long. Similarly, chains can get branched. I will show you the structure of the branch chain. What I mean is, suppose I have a chain like this. When I say it is branched, there may be a branch going out from here, a branch going out from here, and further from here The branch could go out like this. Like in a tree you have branches. Such a chain, can you align parallel to each other? Certainly not. Branching can also be achieved sometimes by irradiating the polymers to gamma rays or X rays. It can be achieved. So that's when sometimes we want to make the material non-crystalline purposely, so it's more pliable, more soft, we do that. Then stereoisomerism is the arrangement of side groups R1, R2, R3, R4 I talked about in the space. Let's first have a look at that. Then we shall come to the copolymers and plasticizers. Arrangement in space. Here I am showing, let us say this is a PVC. One atom is chlorine, other three are hydrogen. Red one is the chlorine, let us say. This is coming on this side, that side, that side. It is coming randomly. There is no regular arrangement. Such an arrangement is called and generally we have this atactic arrangement of the side groups. They are randomly arranged and this can never give me a periodically repeating pattern. So, crystallinity is not possible. Improve the non-crystallinity. By its presence, there will be non-crystallinity in polymers. Alright, let me show the next one. Okay, so I crossed, I think, two of them. Alright, let's go to this. This one where chlorine ones are always on the same side. It can provide me a periodically repeating pattern and can improve the crystallinity. It's called isotactic arrangement. This can improve the crystallinity. Now the third possibility, chlorine comes alternately above, below like that. This can also improve the crystallinity. This is called syndiotactic arrangement. And this stereoisomerism is also called tacticity. Okay. So, this syndiotactic can also give rise to crystallinity, improved crystallinity. Alright, next in the list was copolymers. Copolymer means I have another polymer present in the long chain. Long chain by itself, let us say polyethylene, I have in between a polyvinyl chloride. Here I am showing, well, these are the arrangements which I just showed, atactic arrangement, isotactic arrangement and syndiotactic arrangement. That's I just showed, that's the same thing. It's not so colored, but let's go to the copolymers. Yeah, this is a monomer of, let us say, polyethylene, and the white one is a monomer of polyvinyl chloride, let us say. Black is polyethylene monomer and white is the, or the uncolored one is the polyethylene. So, polyvinyl chloride and polyethylene, they are going monomers randomly distributed. It is called a random copolymer. I cannot find any periodicity in this. It cannot give me crystallinity, that will rather improve the non-crystallinity in the polymer. When it is present alternately, polyvinyl chloride, polyethylene, polyvinyl chloride, polyethylene and so on and so forth, this is an ordered one. Difficult to obtain this, but if it is there, chances of improved crystallinity will be there. In here I have a block of polyvinyl chloride, another block of polyethylene. In other words, these are long chains, not one monomer or two monomers, large number of monomers there. So, this is called the block copolymer. This is also not likely to give me, because segments having the length of the polyvinyl chloride, the polyethylene length and the polyvinyl, they are not the same length, they are the segments are of different lengths. Then just now I talked about the branched chains, here I show you the branched copolymer. This is polyvinyl chloride, on the sides are branched with the polyethylene chains like this. Only thing is, one hydrogen is removed and started to put a chain there, okay, and that becomes a branched copolymer. Copolymer, two of them are existing together. If you look at what I talked about the alloys, this is something similar to substitutional solid solution. This is something similar to substitutional solid solution, okay. All right. The last one we talked about is the presence of plasticizers. Plasticizers are low molecular weight additives put in the polymer. So, by their presence, what they do is they increase the distance between chains. Once the distance between chains is increased, their translational mobility improves, and therefore my polymer becomes more pliable, more soft. As I told you yesterday, PVC is a rigid material, but the PVC pipings or tubes which are used for watering the gardens is very soft. We add some plasticizer to it to make it pliable, more soft. Similarly, you have heard of the celluloid films, the photography you do, the films you use. Basically, cellulose is a very rigid material. Wood consists of cellulose chains which are bound by some glue which is called lignin. This is a rigid material. Only when we add camphor to it, we can make it soft and pliable. This is like a negative film. If this negative film you keep it in the open air for about a month, you will find that it becomes very rigid and crisp. If you try to fold it, it will crack. The camphor has evaporated and that pliability is gone. Camphor, when it was present, it has increased the chain length between, or distance between the chains, that is the cellulose chains, and it has become soft and pliable, right. So, that is what happens to the garden hose also. It keeps lying in the summer and the lawn itself, you will find that in the sun the plasticizer evaporates very fast. It comes to the surface and just goes, because it is a low molecular weight material and it just simply evaporates. And what is left material is a rigid material, so it cracks with juice, that's seasoning takes place, and that's the role of plasticizers. It is similar to what is the role of modifiers, the impurities in silica like soda and lime. They lower the viscosity, means soften the glass. Similarly, here they make the more pliable and more soft plastics by addition of these plasticizers. Thank you.